that we are not aware of our abilities and we always underestimate our capabilities. But when we are put to the test in only challenging situations, they say when things get tough, the tough get going, right? So essentially you're seeing that some of our capabilities which are latent, which are our potential, but it has not been actuated yet. But when we are put in such a situation, for example, you're left in a forest, or you have an aircraft crash and you're trying to get out of a no man's land, some of your abilities that comes into the fore for survival will be amazing, because these survival instincts within us is not just as us as human beings we have learned over this life, but as evolutionary products. Most animal kingdom is on the survival basis that it is trying to extend its life. So we have learned all of this survival instincts, but it's all sleeping within us because we don't need to use it on a day-to-day basis in the way kind of luxurious lifestyles that we live in. But once in a while, when we are put to the test, we have to utilize that, and that's essentially saying that I'm responsible for everything. Doesn't matter what kind of a raising new scenario has come up, I can do that too. And obviously that's what happens with the tortoise. It trundles along, got into the river because it's adaptive. As much as it can go on land, it can go on water, and that's what we call in a lot of aircraft applications as smart structures that I introduced to you as a small subset of multifunctional materials earlier. And then it swam back to the swam to, of course not back, swam to the opposite bank where the finishing line was, and essentially it's a designated reptilian Land Rover primarily, yet amphibious. So that's what you're looking at over there, that it is capable of doing both equally efficiently, and which is what it did. May not be very fast at doing it, but it's capable of doing it nonetheless. So then it, of course, it's not, the finish line is not exactly at the other bank, but a little further away. So it continued walking. All that's there right now is the way it is. So it's a question of accepting the situations as they are, because if you don't accept the situation as it is right now, then you're always complaining about it and not doing anything about a better future. But once you say, anyway it is happening, this is the current situation, how can I think about it, how can I innovatively try to do something about it and make it better. So that's essentially what that is there, an acceptance of what is current at the present, and therefore designing a better future, which is all entirely in your hands. That's what the tortoise did over there. Finish the race. That's essentially the inference that you get from this. Now the takeaway from this third episode is that we have been able to identify for the different subsystems that are there in the overall system unique competencies. Each of them is good at certain thing. Just because it is bad at something doesn't mean it is bad overall. The tortoise is so slow on land, doesn't mean you give up on the tortoise because it has a water swimming capability. On the other hand, the hare was lazy, it took rest. We didn't give up on the hare. Neither did we give up on it now that it has come and stopped at one of the banks. It's not able to go. We know it, so its own capabilities are there, which is why it won the second episode race. But the third episode was won by the tortoise just like in the first episode. And so that's essentially what you're talking about. And what you're talking about from a takeaway point of view is that I'm not the body, mind, or the intellect. So most of the time our identification is with the physical body, with the emotions, or with the intellect. Then we think of ourselves as very, very minuscule entities unable to do a lot of things. We are way beyond just that. Those are the tools that are given to us, and those tools remain even after we die. But what we were is essentially that life, and that life principle, if it takes care of all these three properly and puts it to the appropriate efficient use, then it's unimaginable what all kinds of capabilities that we can have. So essentially what we are doing is to identify the core competencies, and we are changing the playing field itself. That's what the tortoise did. The tortoise saw that on the land it's never going to win. So the only way is by changing the playing field, changing the game, and that's essentially what we are talking about over here, which is essentially a dimensional shift, or what we call as a paradigm shift that happens when we try to identify what kind of a game we are good at playing, and therefore we take that kind of a choice in terms of how we want to go forward to suit the core competency that we have identified within ourselves or within the dynamical system that we are dealing with. So that's where you're going beyond physicality, what we call as metaphysicality. So there's a branch of science called physics, and the reason why we call it physics is it deals with physical bodies. By physical bodies, we mean that it has boundaries. In other words, it starts here, ends here in a spatial sense. It also has a certain time when it was manufactured, when it will be recycled, so it has a certain timeline. Same thing with our physical bodies also, from birth to death, and from in terms of our height, in terms of our width, in terms of our thickness. All these things are limitations. Again, you're talking about in the spatio-temporal sense, it has certain boundaries. To break through those boundaries is when you go beyond physicality. So physics, remember, is a science which studies physical entities, and physical entities are those which have boundaries in spatio-temporal sense. And when you go beyond those boundaries, you no longer are identified with those boundaries. You get to what is meta. And meta is not just the parent body of Facebook, it really means beyond. So you're going to beyond boundaries. So you're essentially talking about beyond physicality. It means you no longer respect those boundary conditions. You're able to transcend those boundary conditions, which is what is the main takeaway from here. So finally, we go on to the episode number 4, where we try to run our imagination even wilder and go to the so-called third approximation. Even though it's episode 4, we are talking of a third approximation because we started approximations from 0th order. So first episode led to 0th order, then slowly we have gone one level up. So fourth episode is going to lead us to the so-called third order approximation. So that's where I come to you with your homework. So I've looked at it from 3 episodes point of view, but I want you to revisit all those 3 episodes because there's no unique way in which this can be written. It's just I'm running my imagination wild to see what I am perceiving in each one of these. Each one of us has our own perceptions. So have a discussion amongst yourself, come up with what appeals to most of you as the best perception of each one of those phrases in the story. And I only went up to the 3rd episode. You have to go all the way up to the 4th episode. I didn't want to do all of it over here. So you complete all the 4 episodes. Don't take it for granted from me, whatever I have given here, that may or may not be the best analogy. So I would like you to go look at your own analogy. So extend this analogy, which we began today's class, to the rest of the fable, as I said, including all the additional episodes. And I want you to leverage not only your own intelligence over here, but also the artificial intelligence that is available to you. And but you, at the end of the day, it's you who make the decision. You take what is the best out of all of them. So use your intuition in order to do that. So yeah, we still have half an hour. Okay, so this is something that is going to apply not only to today's homework, but to all your homeworks throughout this course. It's actually a summary of what I already wrote to you in the email. I've just put it in the form of a slide over here. So all homeworks, as I already mentioned, are team games. That is, all of you do it together. It's a single team, not teams between yourselves. It's in dynamic peer coaching. Think of it as you're helping each other out. Certain things you understand better than your classmate, some they understand better than you. So essentially you're trying to exchange that not just as an information but as an understanding, right? So that's integral to learning, so which is what I want you to focus on. And the only competition for you here is nobody else, not neither in this class nor outside this class, but your own past self. You want to be a better person today than you were yesterday, and you want to be a better person tomorrow than what you're today. And that holds for all aspects of you, including your capabilities with dynamics, with your capabilities of the skill sets, with the tools that you're using in AE2220, right? Now there's certain tips that are there in terms of how you could strategize this whole game, and that's to use all the resources that are available to you, the relevant of course, because there's so much of information overload that sometimes you can get into all kinds of irrelevant things. Make sure that you're looking at the relevant sources, and those include your large language models, your apps, the books, the internet, forums, friends and foes, if you have any, and cite them, okay, not necessarily the friends and foes, but the rest of them, cite them, and in terms of the written as well as the oral presentation that you give, I really want that to come out to where you got it from and how you have interpreted it, and how which parts of it you took and which you didn't have to, what kind of prompt changes you needed to make in order to get to some relevant feedback. So it's a contextual thing that you want to do. It's a setting that personal context for the particular problem is very, very important. So the next tip that I have is in terms of utilizing the resources is to look at their specific input and utility, because this will have some takeaways for your following homeworks, because the way you see how this helps you in the one particular homework, you can also see maybe it's not so helpful in this homework, maybe for a future homework it will be helpful. So that kind of takeaways are also very, very useful over here. And most importantly, I want you to look at the limitations, in particular the AI LLM tools, but even the books that are written in a classical sense. Like for example, we mentioned certain things about some books ignoring the frame of reference in which time derivative is taken, etc. So there are certain very important things which are neglected, some assumptions which may not be stated but actually assumed. But so those kinds of things I want you to bring out as limitations of both the books as well as the other sources that you get information from, and how you eventually overcame them. Then, as I said, the best way to learn is to teach. I have found that out myself, but between yourselves try to mentor each other and try to see how you all as a group can learn better. Then also in this case, for example, you have 4 episodes. You could probably divide that 4 amongst you, like say 2 each. I'm just thinking aloud. It's not necessary. I'm not asking you, you have to do it that way, but just giving an example of how it could probably be done. Then you probably try to see, then you do much more justice to each one of them if you try to divide it into smaller modules and try to split. But everybody needs to understand everybody else what they did, so because you're going to eventually connect that, because if you have made totally different kind of analogy for one episode to another, then it doesn't carry over in terms of the continuity of the story, right? So then internal problem allocation basis has to therefore be based on the core competency, because you understand each of your strengths, so you can probably volunteer and say, I'm good at this, let me do that part, and somebody else might benefit because of that. Okay, so that's another takeaway from the hare and tortoise story itself, that we looked at the tortoise capability on water and the hare's capability on land, and they tried to take advantage of both in the team episode at the 4th episode, which I didn't discuss the analogy for. So then, as I already mentioned, I'm going to be scoring you on for the entire team and not for individuals, and therefore make sure that everybody performs well. So then again, there's this whole gung-ho about on social media and everywhere about be goal oriented. So that's something I don't really want you to be, which is why I give you the answers for the problems. You know the goal already, so you have the goal with you. Don't worry about the goal. What I'm more interested in is what kind of process you use to get to that goal, because that's the methodology, step-by-step methodology. What assumptions you're making, are they valid or not? What are the takeaways? That's what is much, much more important. So please don't be goal oriented, be process oriented, at least for this course. And if you see the benefits of it, you can take it for other courses and life too. That's why the final answers, as I said, are provided for all the questions. Of course, not for this one where I just went through the 3 episodes, but for the remaining ones, the numerical answers will be given for each. And also, as I said, you have the videos from the previous batch. So I want you to improvise. That's where evolution continues to take place. You want to go evolve beyond what the previous batches are to be a better batch, because that's otherwise life is wasted, because we are just doing the same thing which animals were doing and same thing which our ancestors were doing. There's no fun in this whole thing about making the whole process better for ourselves and for our future generations. Future generations, not just children, but our students and so forth, right? Then, as I said, you can use slides or the whiteboard or both. but use slides only as a skeletal props. So you are using them as prompts or props, essentially to have your thought process, so that if you forget something, then you are able to go back to the line of thought and continue with where you left. Do not write the whole thing and keep reading that. I don't want that kind of a slide presentation. That's good for documents, not for PowerPoints or any other kind of presentation that you might be making, Apple Pages or whatever, right? But in oral description, you have to, of course, obviously have the full continuity over there, but the slide design itself should be just very skimpy lists, itemized, not full sentences, etc. Okay, and as I said already, you have to state the assumptions wherever they are invoked, rather than all the set of assumptions at the beginning, and then maybe you're not even using some of them, or you don't know where some of them are being utilized. There's no point. Wherever it is invoked, and the same assumption may be invoked in multiple places, I want you to restate that over there, at least orally, if not in writing, so that you can see the utility of those assumptions in terms of making the problem simpler. So I think we will, I think we still have time. So very quickly I'll go through this. This is required from the formality point of view for all Georgia Tech courses that you're familiar with. So I think I'll not go into reading all of that, just presenting it as a formality. But there are a few points which I found very interesting and might be of very specific importance to this course. So which I just highlighted in yellow over here, which is integrity of our community. And I think that's something best learned in the teamwork that you're going to be doing over here. One is to be able to live that integrity even when you're competing with each other, but now there's no competition. It makes it all the more useful and easy to see that integrity that is there. Integrity in the sense of oneness, but at the same time integrity in the sense of being integrated with the truth in terms of honesty, etc. So that's the honor code that you're also familiar with. Again, I'll not go into the details of that. You're familiar with from various other courses as well. So and again, in terms of the trust that is involved with each other and with me and throughout this particular course, and that's, I think, something that we will live up to. Another very interesting thing that I saw, and I was really proud of my alma mater, Georgia Tech, is because of the word that they used in one of these things, which most engineering institutions and scientific institutions shy away from, which is what I put in bold over there, spiritual, because there's certain dimensions of who we are that we sometimes try to hide and not bring it out to the forth. So I'm really happy that when Georgia Tech talks about well-being, it talks about well-being at all our levels, because we are not just the physical body, we are also the emotions, we are also the intellect, we are also our energies, and we are our spirit. And at the same time, when we are growing, we are trying to address the needs of all of these dimensions of who we are, so that we grow as an entity, as an integral entity, rather than lopsided growth. It will be really funny if one of my hands was growing much bigger and stronger, the other remained weaker or thinner. So it's going to be very lopsided kind of a development. That is quite obvious when you're looking at the physicality asymmetries, but that's what is happening when you're going beyond the physical dimension to the emotional, intellectual dimensions, etc., which is what I really want you to be focused on. And the place where you are in India is really ripe ground to imbibe some of these capabilities. Social justice, of course. Okay, so this is something that I find in the web, a very popular one, many millions of views by Dominic Walliman. I think some of you might have seen some of these things. He does some really very short videos, but gives the overall picture of various things. Of course, it's more tailored for the layman, but it helps us understand the bigger picture, especially when you're venturing into a new subject or a new topic like we are doing with dynamics. We need to understand where it stands in terms of the other aspects of what we are going to learn. So we have briefly touched upon these aspects already, but let me just focus on some of the things. So you look at classical physics over here. So that's what our entire dynamics course will be based on. That's what your statics course was also based on. But that's not the only branch of physics that is very popular and where a lot of effort is being put today. But there is also something called relativity, which we touched upon briefly, where you're going to speeds of comparable to that of light, at least in orders of magnitude that you're looking at. And then you have the other end of the spectrum where you're dealing with very, very tiny particles and getting into particle physics, etc. is looking at quantum physics. Okay, so these are things that we will not be touching upon in this course. Our focus is on classical physics. But beyond these three, there is something else as well, which is what is known as the chasm of ignorance. Okay, the chasm of ignorance is so large, that's what I was mentioning, is 95% of the entire universe, which we don't understand, both in a spatial sense as well as the temporal sense. And this is something that is admitted by all the physicists. It's not something like a viewpoint of somebody, but it's that is the truth that we are looking at as and when we get new information about how the universe itself is behaving in terms of its size, in terms of its growth, etc. So that is the chasm of ignorance, which is not possible to be fulfilled unless you get into the philosophical aspect of what we call as metaphysics. It's for no reason that philosophy is called as metaphysics, because there is physics in it as well, but you're going beyond what is the limitation of physics, which is its boundaries, which is essentially the physicality, and you're going beyond the physicality, which is what a lot of physicists today in some of the top schools as well as the industries which are involved with engineering applications of fundamental physics are looking at. And in terms of the future, what it holds, there are lots of unanswered questions. We already talked about dark energy and dark matter. The reason why it's called dark energy, dark matter is not because of something associated with darkness, but more so because of the ignorance that we are talking about. We don't understand what these are, the energy and the matter, which constitute more than 95% of the energy and matter, and that's the reason why it's so important. And some of the things that people have been working on for a while are like string theory, loop quantum gravity, etc., to understand quantum gravity, which is again one of the unsolved problems of science for us today. Right now, coming back to where we are focused on, it's the Newtonian mechanics, and therefore we are focused on Isaac Newton over there, and that's what we look at in terms of the law of motion. As I said, he's not only a physicist, was not only a physicist, but also a great mathematician. Along with Leibniz, he pretty much invented what all we use as part of calculus today, and that's important. But the more important focus is on the laws of motion, of which we have been talking a lot about the second law of motion. We even talked about the first law, but the even more significant than the first and the second law, the most fundamental law of science, leave alone physics, but of all of science, is the third law of Newton, which is every action has an equal and opposite reaction. That is called as the principle of reciprocity or principle of symmetry, and that's something which is valid even in the micro levels. That is essentially you're talking of quantum physics, etc., whereas all other laws, including Newton's other two laws, will go for a toss when you go to the these extremes of speeds and sizes. But this is something, the third law continues to remain, and that's something where Indian knowledge systems have spent a lot of effort on, what we call as the law of karma, where every action has an equal and opposite reaction, valid not only for objects which are so-called insentient objects, but also for sentient objects like us with life, that what we do, we get back. What we speak, we get back. What we think, we get back. So the scales involved in terms of time might be different, but eventually it comes back, and that's something that we should be aware of. The other important contribution of Newton was the law of universal gravitation. The force due to gravity is F is equal to g/mm by r squared, that you are familiar with. Where r is the distance between the centers of mass of the two bodies, and then we are able to, this is the universal gravitational constant, of course, in the mass of the main body which is exerting the gravitational force, most cases the earth that we are dealing with, but since we are dealing with space dynamics as well, it could be other planets or other satellites of other planets, or the sun even, depending upon the proximity, which is having a lower r because of the 1 by r squared effect being important. So this is what will become your acceleration due to gravity small g, which on the Earth is of course approximately 9.81 meter per second squared in SI system of units, and this is essentially what we call as a body force. And there are many such other body forces. If you go beyond the law of universal gravity, you get into optics, and then you see optics as a part of what is known as electromagnetism. It's just a small spectrum, small part of the overall electromagnetic spectrum is your optic or visible light. When we say visible light, visible to the average human eyes, of course, but many other animals like owls, etc., bats can see beyond those ranges as well. So in spite of all of that, all of what the animal kingdom can actually experience is a very small part of the electromagnetic spectrum. And so beautiful how the electric field and magnetic field have a lot of interaction between them, and the analogies between them, which is all the work of James Clerk Maxwell, who came up with the Maxwell's equations that you might be familiar with. And you see now light being treated as a wave rather than as a photon, a set of photons or particles that we were dealing with earlier. Of course, this continues to be useful for certain aspects of light, understanding light. Then of course the aspects of optics like reflection, refraction, diffraction, etc. And there are a lot of takeaways from those aspects of physics to the variational principles we use in dynamics today. In fact, next class probably I'll talk about a few of those. The Snell's laws of reflection, for example, were actually initially stated as a variational principle, and that's how these two are very different from each other, reflection and refraction, because reflection tends to make sure that the light path is the shortest distance, whereas refraction makes sure when it's going from one medium to another medium, the light takes the path which is the shortest duration, not the shortest distance but the shortest duration, which is why you will see if I have some water in a beaker and I put a spoon, you will see that even though the spoon is straight, looks bent. It's essentially because the time it takes from point A to point B for light to travel is much faster along that bent path rather than the straight path, which is what, because the speeds of light are different in the two different media, the air or vacuum and the water or glass or whatever. Okay, so the refractive index, for example, this glass has a refractive index of 1.74, which is one of the higher refractive indices. I'll come to you, which makes the glass thinner and thinner. So from an engineering perspective, in terms of how many of these things can be utilized, also it's very, very important. So the reason why I brought that is because both these are stationary principles. Whether you're trying to minimize the distance or minimize the time taken for light to travel from point A to point B, both are can be stated as a variational principle. And in fact, a lot of learning for Lagrange, for Hamilton, etc., happened from the optics, because they saw how Snell and others had dealt with optics in terms of variational principles, and those takeaways were there for the case of the mechanics, in particular dynamics. So
I just want to clarify. So you mentioned if light is passing through a higher density medium, it goes slower, and if it's like a curve, like a refractive index, if it's curved, it goes faster. Does that mean that if it's like a low density medium but it's straight, would it go faster than the same medium but curved, or is that not how it works?
It's not necessarily so directly correlated with the density, because there are certain optical properties of each medium. Okay. So for example, glass itself, it could have like this glass and some other glass will have almost the same density, but this will have a higher refractive index compared to some other glass. Okay, there are certain properties in terms of the microstructure of the glass itself, because remember, it's a ceramic, right? So how it is kind of structured at the micro level, how one atom is positioned with respect to the other, how it is bonded with respect to each other, all those things will come into picture. And some of these changes may not change the mass density. They might be the same kilogram per meter cube both, but one of them could have a higher refractive index. So that's also a possibility. But keeping all other things same, yes, density plays some role in terms of the speed of light in each one of them, and therefore how much the bend is.
Okay, so I guess one example of what you're saying is like if you had a tube maybe that was completely lined with like aluminum or some sort of mirror inside, then the light would go way slower even though it's going through air because it's refracting off of all the sides and it would get stuck.
Yeah. So there's both happening over there, because see, when light strikes something, it's not entirely reflected or entirely refracted. So there could be some reflection, some refraction, some diffraction, which is essentially the light spreading out all across. So small percentages of each could be happening, and each of these will be governed by the relative optical properties of each one of those. But what is interesting takeaway from here for our dynamics course is that it is governed by a very interesting physical principle of stationary, the stationary principle, which is essentially minimizing something. In one case it's minimizing the distance, the other case it's minimizing the time. You can very easily see if I just sketch this. Suppose I have let's say a mirror over here, right? And I hit light over here. So then it reflects in such a way that if I draw a normal to this, so the light is coming in over here, which we call as the angle of incidence, and this we call as the angle of reflection. Now all that we are saying is, all Snell said, Snell's law, is that I equal to R. But why it is so is very interesting. If you just take 2 points here, A and B, okay, I want light to go from A to B via the mirror, okay, not directly from A to B, but I want it to go through the mirror. There are many ways in which it could go. For example, it could go to this point and then go to B, or it could go somewhere here and then go to B, etc. But it doesn't take through those paths. It takes only this path where I equal to R. Why? Because if you add this distance, let me call this C, if you add AC plus CB, that will be the shortest distance between A to B, which includes AB and one point on the mirror, any one point on the mirror. So it will not take the C prime or C double prime, because the distance AC prime plus C prime B is bigger than AC plus CB. So the shortest distance is what it takes, and this can be posed as a principle of variation in the calculus of variations, and you can actually minimize that distance and you can get this solution I equal to R. So it's not something that is just based on a physical experimental observation alone, but can be got from a theoretical derivation using a variational principle as well. On the other hand, the other thing that we were talking about was when you have two media, right? So let's say you have water in a beaker. So then you see that when light goes like this, it doesn't continue on the straight path, it actually bends like this, right? So once again I take the same points, and I want light to go from point A to point B. Okay, now you know that the shortest distance is very easily this line, right? The line which directly joins A to B, that's the shortest distance. But it doesn't take that, it goes through this. Because the principle that is governing over here is the principle where the duration it takes from going from point A to point B, you want to minimize that. Okay, so and that can happen because of the different speeds of light in these two media, which could be air and water, or it could be any other media through which light travels. Then you will see that if you actually state this in a variational principle and you go to that, you will see that this is the kind of refraction that will happen. This bending that is called is essentially angle of refraction, because it's not continuing straight but it is bending around. That is essentially what you call as the refraction. So of course this is not a course on optics, but I'm saying that the mathematical techniques or principles that are involved are so widely applicable. It's not restricted to one field or the other, but to a very large range of fields, and especially because of the dual nature that it can be considered both as a wave, as a particle, namely a photon, there are many other interesting things that happens as well, which is beyond the scope of what we are doing here, so I'll not go into the details of that. But this is a nice quick let's say 10 to 15 minute video at the most, where he actually describes all the aspects of this and goes into each one of them in a separate video, etc. It is not meant to be an advertisement for that, but just for us to understand the bigger picture, because whenever we get into a particular topic, like what we are going to do, of course, is to essentially be focused on this topic, we should also understand where it fits into the overall picture. Otherwise, we become like the frog in the well kind of a syndrome, where we say the frog in the well thinks that is the whole world. It thinks there's nothing beyond that. Okay, it's only when the frog comes out of the well it explores and sees, okay, there's a much bigger thing. There's something called the river, something called the ocean, or even a lake for that matter, which was much bigger than its well, right? So that perspective, that bigger perspective you have, then you see where things fit in. And as I said, something which works for something else, in some other field, we might be able to adapt those kinds of procedures or processes in our field and probably do things which are otherwise thought impossible or very difficult and challenging to do. So that's one thing. Then again, if you're looking at, that's all in classical mechanics. Your statics, the dynamics, everything falls under classical mechanics as a fallout of the laws of motion. And then you have the fluid mechanics as well, which is essentially taking from rigid body to something which is fluid in nature, maybe a liquid or gas. So that's why you have flows as well as internal flows, external flows, and also the flow of gas, which is air in this particular example, over the racing car or any car that you have. So then there are things like chaos theory, etc. Again, it's always a lot of interaction between what we call as mathematics and physics. Some of these are more like mathematical techniques or mathematical ways of understanding reality, but mathematics is the language of physics and of most of science, and therefore you will see that some of these concepts are really great at understanding reality in a much better way. For example, the principle of uncertainty that we talked about, something on an extended basis is essentially you're talking about as chaos theory or uncertainty quantification, etc. Again, we said that word dynamics forms a part of thermodynamics too, not only fluid dynamics or solid dynamics, but also thermodynamics, right? So there you're talking about the heat flow that is involved. You bring in the concepts of energy and also entropy, and also the concept of temperature, which is essentially a measure of the average kinetic energy that is involved in the particles making up the flowing fluid, or stationary fluid for that matter, which is essentially a measure of the temperature, etc. And the level of disorder that is there, to put it in the most crudest and simplest way. But there's a whole body of knowledge based on entropy, which is a very interesting concept in the whole overall science, leave alone classical physics, right? So at least from this perspective, within classical physics, we should know where we kind of fit in terms of the dynamics and how it correlates with your statics, which is why I just thought of bringing in this interesting perspective in the first class, so that from the next class onwards we'll be more focused on the engineering dynamics as they take away from the statics that you have already learned. Okay, so the next class, as you know, will be online, synchronous. Chinababu will come here to the reading room to set up for you to be projecting on the screen. Nafis is also familiar with it because we did the same thing in the previous course. So I will be teaching from home, and we'll meet day after tomorrow. Once again, Thursday, of course, we'll meet in person here. Thank you. Okay. Thank you.